Hello friends, in this video we will be continuing with our discussion of the electrical engineering paper 1 in the UPSC engineering service exam conducted in the year 2009. We will be starting our discussion in this video with the 25th question. The previous questions have already been discussed in the previous videos. So let us now move on to the 25th question. Now over here in the 25th question they have given us a circuit and has asked us for the circuit as shown above, what is the value of I. The current I has been marked in the circuit. Now let us analyze this circuit in detail. Over here the circuit has already been redrawn and the question asks us to determine the value of current I. Now moving to the solution, two concepts that we have to keep in mind while trying to solve this question are: the first one, any element in parallel with the ideal voltage source is redundant. Now if we apply this concept, here we have an ideal voltage source and a resistance in parallel with it. So this resistance is redundant. It is as good as having this single voltage source alone. So the next one is any element in series with an ideal current source is redundant. So we can see a ideal current source over here, a 6 ampere current source, and a resistance is connected in series with this current source. So this resistance is redundant and it is as good as having this current source alone without any resistance. So considering these two concepts, we can simplify this circuit as shown over here. This resistance of 3 ohm has been removed since it is redundant, and the series resistance of 4 ohm has been removed over here since it is also redundant. Now we can apply the concept of current source to voltage source transformation. Here we have a current source and the source impedance is in parallel with it. We can convert it into an equivalent voltage source, and that equivalent voltage source has a magnitude that is given by 6 amperes into 1 ohm, that is 6 volts. So the polarity also has been marked correctly in accordance with the direction of current, and the source impedance does not change in value, but it is included in series with this voltage source. Now this circuit can be solved quite easily to find the value of current. The value of current is given by this voltage, that is 6 minus 3, this EMF source, divided by the total resistance, which is 2 plus 1, which gives us 3 by 3, and the current as 1 ampere. So the final answer is current of 1 ampere. Let us now see the options. Here they have given us in option D current of 1 ampere. So this is the correct option. We will now see the 26th question. Dissipation factor tan delta of a capacitor is measured by which bridge? 4 options have been given. Let us see how this question can be solved. Now the 4 options are Anderson bridge, Hayes bridge, Schering bridge, and Wayne bridge. Now Anderson bridge is used to measure inductances having low quality factor. Low quality factor means Q less than 1. Hayes bridge is used to measure inductances having high quality factor Q greater than 10. So these both options are not correct. Now sharing bridge is used to measure capacitances, so this is the correct option. And Wien bridge is used to measure frequency, so this option is also not correct. Let us now see some salient features of sharing bridge and also some of the features of capacitor equivalent circuit. Now over here I have drawn a sharing bridge, and over here is the test capacitor, the capacitor whose parameters have to be measured, and we have the detector. This circuit is excited using a AC source, and we have a variable resistance and capacitance in order to balance this bridge. Now if we were to see the equivalent circuit of a non-ideal capacitor, it would be as shown over here, a capacitor in series with a resistance. This resistance is called as the equivalent series resistance. Now for an ideal capacitor, the value of this resistance would be 0. Now we can consider the impedance triangle according to this circuit. Now over here the hypotenuse would be nothing but the impedance of the circuit, and the adjacent side would be R, and the opposite side would be the capacitive reactance. The angle between the resistance and the impedance would be the power factor angle, and the opposite angle to the power factor angle would be delta. Now this dissipation factor, or also called as loss tangent, is equal to tan delta, and tan delta is, as we note from this figure, R divided by the capacitive reactance, and we obtain tan delta as omega RC. Now the quality factor is equal to 1 by omega RC, provided the circuit is like this. So this loss tangent is nothing but the reciprocal of the quality factor. So these are some salient features of the sharing bridge. Now we'll just see our options, and in the options we have sharing bridge, option C, which is the correct answer. Let us now move on to the 27th question. The characteristic equation of a feedback control system is given by SQ plus 6S square plus 9S plus 4. What is the number of roots in the left half of S plane? They have given us 4 options ranging from 0 to 3. Let us now try to solve this question. Now the given data is the characteristic equation, and the number of roots in the LHS of S plane has to be determined. Now we can find this using Routh-Hurwitz stability criterion, and applying Routh-Hurwitz stability criterion, we first form the Routh array. The given equation, characteristic equation, corresponds to that of a third order system. So we can write over here in the first column of the Routh array the s raised to the third power, s raised to 2, and s raised to 0, which is unity. The first column of the Routh array is formed like that. Now the first row of the Routh array can be formed by looking at the coefficients of s in the characteristic equation, and we write those coefficients in an alternating manner. The coefficient of s cube is unity, and that has been written over here. Now we alternate and jump to s, and the coefficient of s is 9. That is what has been written over here. Now the coefficient of S square is 6. We alternate and move on to the coefficient of S raised to 0 and we obtain it as 4. Now in order to find the coefficients in the third row, we do cross multiplication in a special manner as shown over here. The coefficient of S is 6 into 9 minus 4 into 1 divided by 6. So that is 50 divided by 6, and the coefficient of S to the power 0, which is unity, is obtained in a similar manner by cross multiplication. We do 50 into 6, 50 divided by 6 into 4 minus 6 into 0. The value over here is null, so that is why we get it as 0 divided by 50 by 6. So that is what has been written over here, and the fourth row we get the element as 4. Now we have completed the root array, and we will just see the first column of the root array, and we can observe that there are no sign changes in this first column. The number of sign changes indicates the number of roots of the characteristic equation in the right half of the S-plane. So since we don't have any sign changes, the number of right half plane roots is equal to 0. Now the system given to us is of a third order system, so we have 3 roots in total. Since we don't have any roots in the right half, all the roots would be lying in the left half. So the number of left half plane roots is equal to 3, and 3 is the right answer. We will just see the options. Option A gives the value of 3, and this is the correct answer. We will now see the 28th question. Which one of the following is not a Maxwell's equation? 4 equations have been given. Now let us see the solution to this question. Now the given 4 equations have been shown here, and the Maxwell's 4 equations have been written over here in the integral form as well as in the point form. So we have Maxwell's first equation, the surface integral of the electric flux density is equal to volume integral of the volume charge density, and the corresponding point form indicates that the divergence of electric flux density is equal to the volume charge density. Now the second Maxwell's equation states that the surface integral of the magnetic flux density is equal to 0, and in point form the divergence of magnetic flux density is equal to 0. And in the third Maxwell's equation, the line integral of the electric field intensity is equal to negative of the surface integral of the partial derivative of flux density with respect to time, or in point form the curl of the electric flux intensity is equal to the time derivative of magnetic flux density. And in the fourth equation we have the line integral of magnetic field intensity is equal to the current plus the surface integral of the derivative of electric flux density with respect to time, or in point form, the curl of the magnetic field intensity is equal to the current density plus time derivative of the electric flux density. Now, these are the four equations that have been given. Now let us consider the fourth Maxwell's equation in the point form. So that is what has been written over here. Now this current density J can be replaced as sigma into E, where E is the electric field intensity. This is nothing but a replacement with point form of Ohm's law. And the time derivative of electric flux density can be written in this form. So this is nothing but the first equation which has been provided. Now the second option shows the force, and this is nothing but the Lorentz force equation, Q into E plus V cross B. Now if we were to see the third option provided, this is nothing but straightforward form of the fourth Maxwell's equation, and the fourth option is straightforward Maxwell's second equation in the integral form. So all these three, A, C and D, form Maxwell's equations, but the option B is not a Maxwell's equation, so the option B is the correct answer. Let us look at option B. This is the correct answer. This does not form Maxwell's equation. All the others are one or the other Maxwell's equations. Let us now move on to the 29th question. The unit step response of a system is 1 minus e to the power minus t into 1 plus t u of t. What is the nature of the system in terms of stability? They have given us four options. Let us move to the solution. The given data is the output of the system for a unit step input, and that has been denoted here as y of t, and they have asked us with regard to the stability of the closed loop system. Now to solve this question, first let us take the Laplace transform of the output, that is denoted as y of s, and when we take the Laplace transform, the u of t gets multiplied inside, and this 1 gets replaced as 1 by s, and u of minus t is s plus 1, and t into e to the power minus t is 1 divided by s plus 1 the whole square. This multiplication by time in time domain represents differentiation in the Laplace domain. So this is nothing but a derivative of the second term. The third term is nothing but a derivative of the second term. So we can simplify this, and on simplification we come to this result, which is y of s equal to 1 divided by s into s plus 1 the whole square. Now let us now find out the closed loop transfer function. Closed loop transfer function would be nothing but the output Laplace transform divided by the input Laplace transform. Now the input is a unit step input, its Laplace transform is 1 by s, so we get the closed loop transfer function as 1 divided by s plus 1 the whole square. Now from this we can make out that the closed loop poles of the system are minus 1, thus they are real, repeating, and they are on the left half of S plane. Since they are on the left half of S plane, the system is stable, which means that for a bounded input the response of the system also will be bounded. Now let us see the options given. The option B indicates stable, so this is the correct answer. Now let us move to the 30th question. Diaz novel galvanometer 1 milliampere 50 ohm is to be converted to a 5 ampere ammeter. What is the value of the shunt resistor RSH? Let us try to solve this. Now the given parameters are that of a galvanometer. We wish to convert this galvanometer into an ammeter. The galvanometer current, full scale current, is 1 milliamperes. The resistance is 50 ohms and the ammeter full scale current is 5 amperes, and we are required to find the shunt resistance. Now first we determine the multiplication factor or the multiplying power M, and that is defined as the maximum value of the current that is to be measured divided by the meter current, and that is nothing but 5 ampere divided by 1 milliampere, and the multiplication factor is obtained as 5000. Now the shunt resistance is the meter resistance divided by M minus 1, and that would mean that we can substitute 50 ohm for this Rg and for this M 5000, and the shunt resistance would be 0.01 ohm. Now let us see the answers given. The answer C is given as 0.01 ohm, and this is the correct answer. Let us now move on to the 31st question. In the 31st question, they have given us a circuit, a series RL circuit, and consider the following with respect to the circuit as shown above. VR is equal to 100 root 2 volts, I RMS equal to 2 amperes, inductance L is equal to 0.25 Henry. Which of the above statements are correct? Now, to solve this question, we have drawn the circuit over here. The voltage across the inductance is already provided, that is 150 volts. The source voltage is 250 root 2 sine 300t. Now from the circuit we will draw the phasor diagram. In the phasor diagram shown over here, the source voltage, which is equal to 250 volts, is taken as the reference. Since this is a series RL circuit, the current would be lagging and the power factor angle has been taken as theta, and the current phasor is represented over here. Now the voltage across the resistance VR is shown over here. This has been wrongly marked as VL. It is in fact VR, and the voltage across the inductance is over here. It leads the current by an angle of 90 degrees, and this is equal to 150 volts. Now from the phasor diagram we can see that the source voltage is the root mean square of the voltage across the resistance and the voltage across the inductance. So Vs is equal to root of V square plus VL square. We can substitute the values that are known. Vs is equal to 250 volts and VL is equal to 150 volt, and we obtained VR as 200 volts. VR is the voltage across the resistance. Now the current through the circuit can be determined. It is given by the voltage across the resistance divided by the resistance, which means 200 divided by 100. The value of the resistance has been given as 100 ohms, so the current is 2 amperes. So we have already found out the voltage across the resistance, that is 200 volts, so the first option given to us is not correct. The second option is correct. We have determined the current as 2 amperes. Now let us determine the inductive reactance. The inductive reactance is nothing but the voltage across the inductive reactance divided by the current. So that would be 150 divided by 2 equal to 75 ohms. Now this inductive reactance is equal to omega L, and from the figure we can make out that omega is equal to 300 radians per second. So that can be substituted over here to determine the value of inductance as 0.25 Henry. So of the three options given, the option 2 and option 3 are correct. So we'll just see the options, and option B gives us the correct statements as 2 and 3. So this is the correct answer. Now we can see the 32nd question. Consider the following statements in connection with boundary relations of electric field. In a single medium, electric field is continuous. The second statement is tangential components are the same on both sides of a boundary between two dielectrics. The third statement is tangential electric field at the boundary of a dielectric and a current carrying conductor with finite conductivity is 0. And the fourth statement is normal component of the flux density is continuous across charge-free boundary between two dielectrics. Which of the above statements are correct? This is a question from the electromagnetic theory topic. Let us solve this. Now the four statements given are shown over here. The first statement is that the electric field is continuous in a single medium. Yeah, this is quite clearly understood. Now the discontinuity comes when there is a passage of electric field from one medium to another. So this statement is correct. First statement is correct. Now the second statement is the tangential component of electric field for dielectric boundary is equal. So that is what has been represented over here. Now in order to prove this, that the tangential component is equal, we will apply the Maxwell's third equation, which is nothing but Faraday's laws of electromagnetic induction. So the closed line integral of the electric field is equal to 0. Here there is no change of flux density with respect to time, so it is equal to 0. And here we have considered the boundary between two medium 1 and 2, and the electric field in medium 1 and 2 with the corresponding normal and tangential components represented over here, and this is the loop for the line integral. Now we can do this line integral over this path, and the path dimensions are width of W and height of H. So we can do the integration, and from this integration, the integration step has been shown over here. From the integration we will be able to find out that the tangential component E1 of t is equal to E2 of t. So over a dielectric boundary, the tangential component of electric field is continuous. Now if we consider the third statement, the tangential component of electric field for a dielectric conductor boundary is equal to 0 when the conductivity is not equal to infinity. That means an imperfect conductor. So let us see, for a perfect conductor the electric field inside is equal to 0 and the conductivity will be equal to infinity. So from here itself we can, the previously derived equation itself, we can make out that the tangential component of the electric field in the dielectric medium would be equal to 0, since the tangential component in the two medium are equal. In the dielectric medium it will be equal to 0. So this is only applicable in case the conductivity is equal to infinity. When it is not equal to infinity, which is the case of a imperfect conductor, this statement would not be applicable. So this statement is not correct. Now the fourth statement is the normal component of electric flux density over a dielectric boundary for a charge-free region. This rho s equal to 0 represents a charge-free dielectric boundary is equal. So we can consider a pillbox and apply Gauss law, which is nothing but Maxwell's first equation, and find out that the normal component of electric flux density minus d1 of n into S is the surface area, minus d2 of n, which is the normal component of flux density in the second medium, into the area S is equal to the charge density into the area. So if rho s is equal to 0, the charge density is equal to 0, this equation implies that the normal component of flux density over the two medium is equal to are equal. So this statements 1, 2 and 4 are correct. Third statement is not correct. And if you were to see the options, option C gives us that the statements 1, 2 and 4 are correct. This is the correct option. Now let us see the 33rd question. Consider the following: phase margin, gain margin, maximum overshoot, bandwidth. 4 parameters have been given. Which of the above are the frequency domain specifications required to design a control system? Now the parameters have been given, 4 parameters, and they have asked us which of them are frequency domain specifications. required for control system design. Now we'll just write down all the frequency domain specifications and time domain specifications usually required for design of a control system. Now the frequency domain specifications are phase margin, gain margin, the phase crossover frequency. The gain margin is measured at the phase crossover frequency, and the fourth parameter is the gain crossover frequency. Normally bandwidth is taken as the gain crossover frequency. The phase margin is measured at the gain crossover frequency, and when the frequency domain specifications are given, usually the design is by Bode plot. Now if we are to consider the time domain specifications, the peak overshoot, settling time, rise time are the usual parameters that are specified, and in such cases we usually do the design by root locus method. Now in the four parameters that are given, phase margin, gain margin and bandwidth are frequency domain parameters, and the third parameter, maximum overshoot, is a time domain specification. So the parameters 1, 2 and 4 are correct. So we'll just see the options. 1, 2 and 4, option D is the correct option. Now let us see the 34th question. 0 to 300 volt voltmeter has an error of plus or minus 2% of the full scale deflection. What is the range of readings if true voltage is 30 volts? Now to solve this question, first we write the given voltmeter specifications. The range has been given as 0 to 300 volt. The percentage error has been specified as a percentage of the full scale deflection, and it is given as plus or minus 2%. Now the true reading has been given as 30 volts, and we are required to determine the range of readings for this true reading. Now the error over here is specified as a percentage of the full scale deflection, so the error can be determined, which is plus or minus 2% of 300 volt. 300 volt is the full scale deflection. Now that would mean the error is plus or minus 6 volts. Now the range of the reading when the true voltage is 30 volts would be the upper voltage. The upper reading would be the true voltage plus the error, which is 36 volt, and the lower reading would be the true voltage minus the error, which is 24 volts. So the reading of the instrument can anywhere be between 36 volts and 24 volts when the actual measurand or the true voltage is 30 volts. So 24 volts and 36 volts is the correct option, which is option A, and this is the correct option. Let us now see the 35th question. A network function Z of S equal to V of S divided by I of S has a single pole at S equal to minus 1 divided by root 3 and a single zero at S equal to minus root 3. If the excitation V of t is equal to sin t, then what is the angle of lead or lag of the current? Four options have been given. Let us try to solve this problem. Now the given data is the network transfer function Z of S, and Z of S has a single pole at S equal to minus 1 divided by root 3 and a single zero at S equal to minus root 3. Now the excitation has been given as V of t is equal to sin t or sin omega t with omega equal to 1 radians per second, and we are required to find the angle of I of t, Now the network function from the given data can be written as z of s equal to s plus root 3 divided by s plus 1 by root 3. So z of s has a 0 at minus root 3 and a pole at minus 1 by root 3. Now to determine the frequency domain behavior of this network function, we can substitute s equal to j omega, and that is what has been done over here. And further we can substitute omega equal to 1 radians per second, since our excitation v of t is equal to sine t, and now we determine the angle of z of j of omega, which is nothing but the angle of the numerator minus the angle of the denominator. Now the angle of the numerator, j plus root 3, is obtained as 30 degrees, and the angle of the denominator, j plus 1 by root 3, is obtained as 60 degrees. So angle of z of j of omega is equal to 30 minus 60 is equal to minus 30 degrees. Now the network function has been defined as z of s equal to v of s divided by I of s. Now it follows that I of s divided by v of s is equal to reciprocal of z of s. Now the angle of reciprocal of z of j of omega would be nothing but the negative of the angle, and that would mean it is plus 30 degrees. So we will apply the property of sinusoidal response of a transfer function, which means that the transfer function, when subject to a sinusoidal input, would produce a sinusoidal output with the same frequency and with a phase shift difference and a magnitude difference. Now here we are required to find out the phase shift. Now over here we have found out already the angle of the reciprocal of the network transfer function, and from that we can make out that the angle of I of s would be plus 30 degrees, and that is a 30 degree lead, which means the current leads the applied voltage by 30 degrees, and the option A provides such an answer, and this is the correct answer. Now moving on to the 36th question. Magnetically hard materials do not possess which of the following characteristics? 4 options have been given. We will solve this question. Now, of the 4 options, in order to analyze these options, we will first draw the BH curve for soft and hard magnetic materials. Now over here I have drawn the BH curve of the hard magnetic materials. So we can see over here that such materials have a high retentivity, a good amount of remnant flux, and high coercivity. So hard magnetic materials are generally used to make permanent magnets, and their BH curve loop area is also very high. Now if we were to see the BH curve of a soft magnetic material, we can see that the remnant flux is very small, the coercivity is small, as well as the area enclosed is also small. Now the area enclosed indicates the hysteresis loss. So soft magnetic materials have low hysteresis loss and are hence used to make temporary magnets. So if we were to analyze the options, the first option A, high retentivity, is a correct option. It is a property of the hard magnetic material. Now the second option B, high coercivity, it is also shown by hard magnetic materials. And the option C, strong reluctance. Now it is a property of hard magnetic materials to show a higher reluctance than soft magnetic materials. They generally have lower relative permeability compared to soft magnetic materials. So if we go to the fourth option, zero differential permeability. Now we'll see what is differential permeability, and over here we have written the equation relating flux density and the magnetic field intensity or the magnetizing force, and the mu is obtained as B by H. Now differential permeability, this mu is nothing but permeability, and differential permeability is the change in flux density divided by the change in magnetizing force or magnetic field intensity, which indicates the slope of the BS curve. Now from the figure itself we can make out that the slope of the BS curve is not equal to 0, so this option is not correct. And in the question they have asked us which is the wrong option. So the A, B, C are correct, D is wrong, and hence D, zero differential permeability, is not a characteristic of magnetically hard materials. So D is the correct option.